Good morning, and welcome to this Conservation Applied Research and Development, or CARD webinar, which is going to discuss the potential for energy savings with residential multi-zoned air distribution systems. Thanks for joining us today. I'm Mary Sue Lobenstein, and I'm the Energy Conservation and Research Planner at the Minnesota Department of Commerce, Division of Energy Resources. In that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill the gaps. The CARD program is a major tool of that work. With me today is Adoy Day, who is an energy planner principal and at the Conservation Improvement Program unit at the Minnesota Department of Commerce. Adoy provides oversight and regulation for natural gas and electric utility efficiency programs as part of the implementation of Minnesota's Energy Efficiency Resource Standard. He has research experience in public policy, computational modeling, and econometric analysis. He is moderating the Q&A portion of our webinar today. Our presenter is Dave Bohack. Dave is the Senior Director of Research at the Center for Energy and Environment. In that role, Dave has directed a variety of applied research and program development projects, including many for the U.S. Department of Energy, ASHRAE, and the CARD program. He has more than 35 years experience in energy efficiency and indoor air quality, with an emphasis on advanced diagnostics and monitoring methods. Welcome, Dave. We look forward to the presentation today. Before we start, I'd like to go over a few webinar basics. These should be familiar with a lot of you. All attendees will be in listen-only mode, and we'll try to answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send to all panelists. We'll do our best to answer all questions within the time allocated, but if for some reason we don't get to some, we'll answer them after the webinar. This webinar is being recorded and will be available on the department's website at a later date. The slide set from the webinar will also be available. Just to provide some context, this webinar is one in an ongoing series that's designed to kind of summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal, and about $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their conservation improvement portfolios. As you can see by this pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is the residential sector, and we'll discuss results from a recent CARD project that assessed the energy savings opportunity for residential multi-zone air systems. Now I'm going to turn it over to Dave, who'll start our presentation.
Thanks for that introduction. As Mary Sue indicated, I'm going to be discussing the results of a white paper study that we conducted on residential multi-zoned or zoned air distribution systems. For those of you who aren't familiar with us, the Center for Energy and Environment is a nonprofit organization that promotes energy efficiency to strengthen the economy while improving the environment. We conduct research and develop programs so that business can operate more efficiently and profitably. Government agencies and nonprofits spend less on utilities and functions. Households save money and improve comfort, and utilities can achieve their energy saving goals at least cost. As with all CE research projects, this was a team effort. Ani Durva had the biggest role. He performed the literature review, conducted the surveys, and conducted the building energy modeling. Dee Swee guided the energy modeling, and Mason Miller processed the temperature data from previous projects. So I'm going to start out with some quick background on multi-zone systems. Next, I'll describe our research objectives. Following that, I'll discuss the methodology and results of our technology and market assessment. Then I'll describe the building energy simulation model that we developed for the prototype houses and the modeling results. And we'll wrap up things by offering some concluding remarks and present all the future work that we hope can be pursued based on what we learned in this project. So as far as what a multi-zone system is, for this project, we only focused on central air distribution multi-zone systems. As shown in the diagram, there's a central air handler provided by a furnace or a heat pump. And then the supply ducts branch off to each of the house zones. Most often there is a zone for each floor, and a mechanical damper is installed in each of the supply ducts, and a thermostat or temperature is located in each zone. When a zone needs heating or cooling, the supply damper is opened and the furnace or heat pump is activated. More than one zone can be active at a time. For higher efficiency systems, the system capacity is varied depending on the number of active zones, and there are no return dampers. So just to be clear, this project did not include multi-zone hydronic systems or multi-split heat pumps, just these central air distribution systems. So here's a couple of examples of installed systems. The red ovals indicate the zone dampers located in the supply branches directly above the furnace and a coil. So the question we are hoping to achieve, or what problem we are trying to solve with these systems, we're looking for improved comfort or temperature control and energy savings. As I'm sure you've all experienced at times when the basement or upper level of your house is warmer or colder than the first floor, central air furnaces and heat pumps are controlled by the temperature in one location, typically the first floor. The airflow in the supply ducts are designed to distribute heating or cooling that matches the loads in each part of the house. And unfortunately, most systems aren't properly balanced, or the relative loads in each part of the house change by time of day or season. For example, the house on the left shows a typical summer situation where there isn't enough cooling in the second floor and it's warm. There is more cooling that's needed in the basement and it's cold. So the second floor can be uncomfortable, and we are using energy to cool a basement that doesn't really need cooling. The diagram on the right shows a winter situation where the second floor is overheated, causing more energy to be used than needed. The basement is cooler than desired. This occurs because the single zone air distribution system has a fixed amount of air that's provided to each section of the house. Sometimes the amount of air to each branch wasn't really set properly to begin with, and then in addition, the fraction of supply air needed in each part of the house can change throughout the day. For example, you could have a portion of the house with more southern windows where the cooling load may be greater and heating load reduced on sunny days. In addition, colder days, the thermal stack effect will increase cold air infiltration in the lower level of the house and have little or no infiltration in the upper level. Finally, as ground temperatures change through the seasons, the basement heating and cooling load changes. So just a little note on previous studies, there have been published information on multi-zone systems. When we were starting this project, our initial review indicated the research focused primarily on cooling energy savings with limited study of space heating savings for cold climates. So our objectives for this project were: 1, review the published information, 2, describe the current market in Minnesota, and 3, model heating and cooling energy use for prototype Minnesota houses, and then generate recommendations. Is there enough information on the savings that we could generate a TRM or technical reference manual measure? Is there enough information to be able to estimate potential energy savings for existing and new Minnesota homes? And then finally, recommend future research, what's necessary to accurately determine savings and improve market penetration. So we started the project with a technical and market assessment that included a review of product information from 8 major manufacturers and a thorough literature review. Our market assessment included interviews with equipment distributors and contractors. We also obtained information on U.S. utility efficiency programs for multi-zone systems and contacted Minnesota utilities to determine their level of interest in the systems and the potential for reducing energy savings. So as far as the information that we got from manufacturers, we reviewed product information from 8 major manufacturers and found that 7 had kind of package zoning equipment, and the 8th has systems that can work with third-party manufacturer zoning equipment. So really, all 8 major manufacturers have zoning systems. Most of the furnaces and heat pumps have variable capacity, but some have only 2 stages. The packaged equipment use wired dampers, and almost all of them have smartphone apps for control. And depending on the manufacturers, the systems can control anywhere from 3 to 16 zones. We also researched equipment from third-party manufacturers and found 6 of those manufacturers that have zoning equipment. The final report summarizes information from 10 key references that we found in our literature review. For one, some of the key information that we found, we did identify builder and mechanical zoning design guides that were generated by Natural Resources Canada and CanMet Energy, along with field studies that they produced. There was a nice modeling study generated by NYU and Purdue that reported cooling energy savings that range from 36 to 51% for the average household, but little space heating savings. On a couple of lab studies, one highlighted the importance of duct leakage and insulated ducts for unconditioned spaces, and the other looked at the impact of closing registers on duct pressures and leakage. And they kind of both concluded that closing registers may not result in energy savings depending on duct leakage. Finally, a CanMet Energy study of utility demand control found 17% reduction in AC and air handler load by controlling just the top level for cooling. And another study found that in some circumstances, smart damper systems resulted in larger duct losses and lower airflow rates, which decreased total system efficiency. As far as regarding the interviews that we conducted with 5 distributors and 5 contractors for installation, all indicated that multi-zone systems were much more common in high-end new construction, less common in retrofits. We asked about the percentage of homes that have systems, and the responses range from anywhere from 10 to 50% of new homes are using multi-zone systems, with an average of about 25%. And that's consistent with a recent Minnesota New Home Energy Code study that found that about 25% of new homes have multi-zone systems. As far as the zoning that's required, all the contractors agreed that high efficiency results by using communicating variable speed systems. A dump zone can be used for single speed, but isn't as effective. The benefits, primarily, they indicated that comfort was the primary benefit and direct control. Energy savings because was seen as being less impactful or important. The drawbacks all express that cost and the zoning setup as being challenges for these systems, especially in existing homes, due to the general absence of separate trunk lines to each zones. Regarding the potential for market growth, we got kind of mixed responses, with some distributors and contractors indicating that the market was increased, some saying it was decreasing. A few indicated that the air source heat pump mini splits were becoming more common and may reduce the market in the future. They did suggest that utility incentives could assist with market growth. So we reached out to 15 or 11 utilities in different regions in the U.S., and what we found was that none of the utilities had programs for multi-zone systems or offered efficiency incentives for the systems. 5 of the utilities had conducted pilot projects. Unfortunately, there was not any published information for any of the public projects, and for those utilities, none of them had decided to implement an incentive program. I'm still in the process of getting feedback from the Minnesota utilities. In general, all of them that I've received so far are aware of multi-zone systems, have interests in them, and believe that there should be some energy savings that could be reduced or generated by multi-zone systems. So switching gears here a little bit, talk about our building energy modeling. We use building energy simulations to evaluate the potential heating and cooling energy savings of multi-zone systems. We develop models for prototype 1- and 2-story houses with insulation and air leakage consistent with either new or existing houses. Each of the models was run with a single zone system and a multi-zone system separately. Then we pulled data from previous residential studies to confirm that the zone temperatures produced by the models were representative of trends seen in actual houses. So we identified 6 houses from previous studies that we had run where we had air temperature measurements at each floor of the house over multiple seasons. This table shows the key information for the 6 houses. Half the houses were 2-story and half were 1-story. 5 of the houses were in the metro area. So one drawback to the sample is that only one house was built after 1940, and that's not ideal since the multi-zone systems are primarily being installed in new homes. But we did feel that this would provide important information. So here are the temperatures results from one of the 2-story houses. This site is about 1,300 square foot house located in Fergus Falls. It was constructed in 2002. It's 3 bedrooms and a finished basement. And I should say for all 6 houses, the thermostat was located in the first floor. These 2 charts show 1 week of measured temperature data. In each chart, the black line is the outside temperature, blue is the basement, green is the first floor, and red the second floor. The chart to the upper left shows temperatures from late fall with outside temperatures that dip down into the mid-30s. The second floor temperature tracks the first floor very closely over the entire week. The basement tracks the first floor but is consistently cooler. For the chart on the lower right that shows a week of summertime temperatures, the second floor is often warmer than the first floor, indicating that there isn't enough cooling getting to the second floor. In addition, the basement is considerably overcooled. It's often 15 degrees cooler than the first floor. So this is a box and whisker plot for all the data that we collected for Site 3. You'll be seeing a lot of these box and whisker plots with this presentation. The data was first sorted into 10-degree outside temperature bins, and then for each box, the median is represented by the horizontal line within the box. The X is the average. And then the bottom and the top of the box are the first and third quartiles, and the end of the whiskers are local minimums and maximums. The colors represented the same floors as those used for the weekly plots, with blue being basement, green first floor, red second floor. So you can see that throughout the heating season, the first and second floor temperatures are very similar. During the summer, the second floor is slightly above the first floor temperature. The basement is always cooler than the first floors, and the difference is greater in the summer. For this house, a multi-zone system would produce a warmer basement temperature, which would increase space heating energy use, but decrease cooling energy. Site 2 is a 1.5-story, about 1,000 square foot house located in Minneapolis that was constructed in 1924. It has an unfinished basement. It is likely that the second floor was poorly insulated and leaky, which is pretty common for 1.5-story homes. In mild weather, when the outside temperature is between 50 and 70 degrees, the second floor temperature is at or above the first floor temperature. As it gets colder outside, the second floor temperature drops below the first floor, and when the outside temperature is below 30, the second floor temperature is at least 5 degrees below the first floor. So the opposite occurs for the summer, suggesting that the second floor is not getting enough heating and cooling relative to the first floor. The basement temperature is always below the first floor. So this is a situation where a multi-zone system should improve comfort while creating somewhat higher energy use in the winter and about the same or lower electric use in the summer. Site 4 is another 2-story, 1,800 square foot house located in Minneapolis that was constructed in 1925, has 4 bedrooms and a finished basement. This occupant sets their thermostat to 70 degrees in the winter and sets back to 67 overnight. They keep the set point around 76 in the summer, and a geofencing feature sets up the temperature when they're not at home. Due to the setbacks, the first floor temperature decreases somewhat with colder outside temperatures in the winter and increases with hotter outside temperatures in the summer. The variations in the second floor and the basement are similar to the previous example, so it's expected that a multi-zone system would improve comfort, but increasing heating energy use and possibly decreasing cooling energy use. So I have a couple of examples on the 1-story houses. This one was built in 1940 and has a partially finished basement. So this is the one example where the basement is actually overheated in the winter. The basement is also overcooled in the summer. So you would expect that a multi-zone system could improve comfort and it would produce both heating and cooling energy savings for this house. This would be a win-win-win for a multi-zone system. Another one-story house, this one was built in 1932 and has a partially finished basement. You can see when the outside temperature is below 20 degrees, the basement, 20 degrees outside, the basement is more than 10 degrees colder than the first floor. So this table summarizes the winter season temperatures for the 6 houses. The columns with the blue, green, and red values are the average basement, first floor, and second floor temperatures, respectively. The columns shaded blue or red are the difference between the first floor and the basement or the second floor temperatures. So the blue shaded cells indicate the zone temperature below the first floor. And you can see there's only one situation where the basement or second floor is overheated, and that was the site number 2, the one-story houses. On average, the basements were 4 degrees below that from the first floor, and the second floors were 7 degrees below. So it's important to note this is a relatively small sample of primarily older houses. So here's the results for the summer data using the same color coding. All of the basements were overcooled with an average temperature that was 6 degrees colder than the first floor. All of the second floors were undercooled with an average temperature of about 3 degrees warmer than the first floor. So it's likely the multi-zone system would not only make the houses more comfortable, but also save energy for these homes. So now we'll switch gears and discuss the building energy model results. So the objective was to evaluate the potential energy savings for a multi-zone system compared to a single zone system. You might be thinking that we can just simply use energy models like we do for resident ratings of new homes. Can't we just kind of simply use those models to predict savings? Unfortunately, those models don't have the capability to evaluate energy savings from a multi-zone system. Typically, it's assumed that the house has one uniform temperature that is controlled by a single thermostat and a single heating and cooling system. It is possible to break the house into separate zones and put different heating and cooling systems in each zone. However, you would need to know the temperature of each zone for a single zone system and a multi-zone system in order to estimate the difference in energy use. These models don't have the capability to determine the basement and second floor temperatures for a single zone system that's being controlled off the first floor temperature. So to address that need, we developed models that could determine basement and second floor temperatures for a single zone distribution system. We used Energy Plus for the simulations and determined the hourly airflow rates from Contam multi-zone airflow models. We generated models for 1- and 2-story houses. Each of those 2 models had one configuration with insulation, and air leakage consistent with new home code requirements, and another with levels that were typical of 1950s construction. For each of the models, we ran the simulations for a single zone and multi-zone distribution system, and you can define the details of the model configuration in the final report. With Energy Plus, the nice thing, you can specify hourly variations in internal loads and heat gain for each zone, and it determines solar gains by zone. You can also import hourly air infiltration by zone and airflows between zones. So as I indicated, we use Contam program developed by NIST to compute hourly infiltration and airflows between zones. This chart shows the house total infiltration by outside temperature. You can see that the thermal stack effect causes infiltration to increase as the outside temperature gets colder and warmer than the inside temperature. The large variation in infiltration for each outside temperature is caused by wind. So the lowest levels have 0 wind, and then higher levels of wind increase the infiltration above that. So this is a significant improvement over assuming a constant level of infiltration and was necessary for our modeling. What's even more important is that the Contam provides infiltration by zone, and you can see the variation with outside temperature is quite different for each level of the house. The basement infiltration is shown by the chart in the lower right. It's heavily influenced by the thermal stack effect, and the basement infiltration during the winter is greater than that for the first floor, even though the first floor is leakier. The first floor infiltration is impacted a bit more by wind than the basement infiltration is. What's most important is that the second floor infiltration actually decreases with colder outside temperature. That is because when it's cold outside, the air tends to infiltrate in the lower level of the house and leave through the upper part. So as outside temperatures get colder, the air infiltration load for the basement increases and it decreases for the second floor, again causing that difference in the heating and cooling loads by zone. So this can drive the second floor temperature to be higher in colder weather. This chart shows the air movement between zones. So for milder weather, there is limited air movement between zones. In colder weather, the house air moves from air from the lower to the upper levels of the house, and then the opposite occurs in warmer weather. So we use Energy Plus to generate the hourly space heating and cooling energy use, but it also generates zone temperatures. This chart shows a box and whisker plot for the zone temperatures for a multi-zone system in a new two-story house. The winter set point is constant at 70 degrees and the summer is constant at 78. So there is weather when the first bar temperature goes above 70 degrees set point, and that's because we didn't AC kick in until the outside temperature was above 60 degrees. So it's interesting to note here that the basement temperature is below the set point for almost the entire summer. This indicates that almost no cooling is required for the basement in the summer, and any cooling provided to the basement is just going to be simply wasted energy and overcool the basement. So Energy Plus generated the distribution of supply air to each of the three zones. There's an auto calc feature for it, and we use that as our baseline configuration for supply airflow by zone. The first floor temperature is similar to that for the multi-zone system. So the first floor is in green. The basement temperature is similar to that for the measurements in Minnesota houses. The basement temperature is lower than the first floor, and the difference becomes greater with colder and warmer outside temperatures. The second floor temperature is also cooler than the first floor in mild and warm weather. However, it rises above the first floor temperature in colder weather. With the underheating in the winter and the overcooling in the summer, you would expect a multi-zone system to probably use greater amounts of energy than the single zone system in the winter and less in the summer. So we went through a number of changes to the supply air distribution to try to produce basement and second floor temperatures that were close to the set point. In every case, we kept the total supply airflow the same. In this case, we increased the basement supply air by 50 CFM and decreased the first floor supply by 50 CFM. In real practice, this would be achieved by manually adjusting the the zone duct balancing dampers. You can see that the basement temperature was closer, but not quite up to the set point in the winter. The second floor temperature increased since the supply to the second floor stayed the same and the first floor supply decreased. You can see that the second floor temperature is below the first floor in mild weather, but above it in colder weather. So here's a case where the basement airflow was increased by 150, and again, the first floor flow was decreased by 150. The basement and second floor temperature are near the set point in the 30 to 40 degree weather, but they get considerably higher in colder weather. So although we didn't see this in our measurement, I know people who live in houses that have uncomfortably warm second floors in colder weather, and it's due to this kind of phenomenon. So this shows the same charts, but just kind of a side-by-side comparison of the zone temperatures with outside temperature for the baseline configuration of the supply air. The first floor temperature is at set point for both configurations, but the zone temperatures are quite different. We found it was not possible to select a distribution of supply air to the zones that provided basement and second floor temperatures that stayed constant and were close to the set point over the heating and cooling season. So what we did was compile the energy use and zone temperature data for the multi-zone system and for the various configurations of supply air for the single zone system. So this chart has quite a bit of information in it, so bear with me a little bit. The bars indicate the heating season gas use. The solid yellow bars indicate the use for 6 different configurations of supply air for the single zone system. And then the dash bar on the right is the gas use for the multi-zone system. The blue, green, and red dashed lines are average zone temperatures for each configuration. At the top is the percent change in the gas use of the single zone systems from the multi-zone system. So you can see the gas use for the baseline single zone system is 356 therms, which is actually 15% less than that for the multi-zone system. The single zone energy use is lower because both the basement and the second floor temperatures are below the set point. In other words, the zones are underheated. As the supply air distribution is changed, the basement and second floor temperatures increase, and so does the energy use. When the basement supply air is increased by 150 CFM, the basement and second floor are overheated, and the single zone energy use is actually 8% greater than that for the multi-zone system. So that's the highest yellow bar you see there at 451 therms. So this chart that also shows that there's a strong relationship between the zone temperatures and the heating energy use. This is a similar chart for the summer or cooling season results. In this case, the single zone system is overcooling both the basement and the second floor for all supply air configurations. So the single zone are the purple bars again, and then the hashed purple to the right is the multi-zone baseline configuration. The basement temperature varies from 70 to 65 degrees for the single zone system, and the second floor varies from about 70 to 75 degrees. So the multi-zone system has the lowest electrical energy use of 1,676 kilowatt hours, and it produces electrical savings from 31 to 66% over the single zone system, depending on the supply air configuration. So I don't have time today to go through all of the results for each one of the models, but I've summarized the overall results from the 4 models. So first, the difference in heating and cooling energy use between a multi-zone and a single zone system primarily depends on the single zone system performance. If zones are overheating, there's going to be heating energy savings. And if it's underheated, the multi-zone energy use will be greater. Second, we found that the percent energy savings were linearly related to the difference between the first floor temperature and the temperature in the other zones. However, the percent savings was different for the existing and the new home configurations. For existing homes, the savings were about changed by about 2.5% per degree difference in the zone temperatures, and it was 6.4% for the new homes. What this means is that if a single zone system overheats the basement and second floor by an average of 1 degree, a multi-zone system would produce 6.4% savings for a new home. For our measurements in the 6 older homes, only 1 basement was overheated, and none of the 3 second floors were overheated. So for those houses, you'd expect a multi-zone system produce improved comfort, but it would also produce higher energy use, except for the one house that had an overheated basement. However, we really need to look at measurements in new homes to better estimate savings, and we need to study the impact of insulation level and air leakage on the percent savings that you get. We did a similar analysis for the summer cooling season, and that showed 9.9% electric energy savings per degree for existing homes and a 6.2% savings per degree for new homes. Since all basements are overcooled and by about twice as much as the second floors, for these are the 6 houses that we measured, we would expect cooling energy savings for older homes. Again, we need temperature measurements in new homes in order to be able to determine the savings for new homes. So another benefit to multi-zone system is the ability to set back temperatures for individual zones instead of the that are not being used, instead of having to set back the temperature for the entire house. So we looked at a typical night setback for all zones and found about 15% heating savings for new homes and 12% for existing homes. We also looked at setting back only the basement temperature, assuming that it was occupied from about 2 in the afternoon and 10 p.m. in the evening. The rest of the time we did a setback, and that way the setback was from 10 p.m. in the evening all the way through the night until 2 o'clock in the afternoon the next day. And that actually produced similar savings as the night setback. So that means that you could set back only the basement um, for a greater amount of time and still get similar savings as what you get from having to set back the entire house. Now, when you combine both the night setback and the basement setback, you can get heating energy savings as great as 24% for new homes and 17% for existing homes. So to review the key findings or our conclusions, in our literature review, we found a modeling study that predicted or computed 36 to 51% cooling savings, but little heating savings. A utility load control study found 17% demand savings by controlling only one zone. And the lab studies of ducts where the ducts were in unconditioned spaces found that duct leakage can cause multi-zone systems to increase energy use. When we looked at equipment that was available, 7 of the 8 major manufacturers had prepackaged multi-zone systems. They can control from 3 to 16 zones depending on the manufacturers. Most have variable capacity. And we also found 6 third-party manufacturers that provide zoning equipment. The interviews that we conducted with distributors and contractors, we found that the zoning systems were being primarily used in new constructions where they're installed in about a quarter of the new homes, which is a higher fraction that I would have expected. And this is primarily in larger, higher-end houses. No U.S. or Minnesota utilities currently have incentive programs for multi-zone equipment. From our temperature measurements in 6 mostly older homes, we found only 1 basement that was overheated in the winter and no second floors that were overheated in the winter. Our model results indicated that, well, I should also note that in the summertime, all the basements were overcooled. And for the 3 houses we had with second floors, all the second floors were undercooled. Our model results indicated that the multi-zone energy savings is primarily a function of the zone temperatures produced by kind of a single zone system. The heating savings was about 6.4% per degree of average temperatures for the basement and the second floors, and it was about 6.2% per degree for the cooling savings. We looked at different setback scenarios, and we found that setting back only the basement temperature produced heating savings of 8 and 18%, and that we could combine that with a nighttime setback and produce 17% to 24% savings. And we also looked at savings of setbacks for cooling energy, and that information is in the final report. So as far as our recommendations, the modeling confirmed that multi-zone systems can save both heating and cooling energy when the zones would be overheated or cooled by a single zone, overheated or overcooled by a single zone system. The systems are primarily being installed in new construction, so I think the incentive programs should probably focus on that market. The savings are dependent on zone temperatures produced by single zone systems, and we need field studies to establish potential energy savings for new homes and possibly some additional monitoring or modeling for those homes. As far as future work goes, those field studies of new homes should include measurements of zone temperatures as the distribution of supply areas varied to help confirm the results that we had gotten with our models. And then zone temperatures for a large sample of new homes are necessary in order to establish what the potential is for the energy savings of a multi-zone system over single zone systems. And then a final confirmation of savings could be obtained by converting single zone systems to multi-zone and comparing the pre-post energy use. And with that, that wraps up the webinar.
Great. Thanks, Dave, for that great presentation. If you have not already done so, please type any additional questions into the Q&A panel and send them to all panelists. Adoy, do you have questions for Dave at this point?
Hi. So thanks, Dave, for that wonderful presentation. I'd like to get us off started with a question here. What do you think are the barriers to having utility incentive programs for multi-zone systems?
So yeah, I think as our recommendations kind of for future work indicated, I think we need to be able to establish what the potential energy savings are for multi-zone systems, compared to single zone, and we need the field data for air temperatures in new homes in order to confirm what those expectations are. So we start doing some field studies, and we find that most of the new homes have second floors that are being overheated. Then I think there's a good potential for heating energy savings, and we would expect there to be cooling energy savings in most new homes, but we really need to do the temperature measurements in order to be able to establish what the potential savings are.
Thank you, Dave. We received another question. The attendee says, great presentation, really well put together. Did the team look at the energy impacts of various multi-zone HVAC configurations, that is dump zone versus runaround loop versus modulating air handlers? I assume the answers are bad, bad, good, but anything more specific?
So the short answer is no, we didn't. The feedback that we had gotten, or the information that we had seen from the previous work that had been done, was that you really needed the variable capacity systems that adjust airflow and heating and cooling capacity with the number of zones that are active in order to achieve kind of proper comfort and energy savings. So we didn't look at the kind of the dump zone type of configurations.
Thanks. Another interesting question, the attendee asks, do you think some or all of the energy savings could be achieved through manually opening or closing the vents seasonally?
Yes, certainly. I mean, I've seen houses where there's dampers that have a winter and a summer setting, down in the basements and or the ductwork in the basement. And so I think you could overcome some of these issues with a seasonal, or at least a heating and cooling adjustment. Potentially, you could also do this by adjusting the manual dampers as it gets colder outside. I guess the question is do you think homeowners would make those adjustments themselves in a consistent way to produce the same kind of impact? And I would think probably most homeowners wouldn't. And the other side of this too is I think there are seasonal variations, that occur, but also, there are kind of hour by hour variations that occur that are going to cause kind of similar issues of, either could have a, quick drop in temperature, or the variations in load that you get into a house on a sunny versus a cloudy day.
Thanks. Another question we have, in general, at least in Minnesota, are we using the forced air systems to distribute ventilation to all habitable rooms? So if the air handler is running continuously, or at least for a significant number of hours, how would this change the savings? Also, if you move to a multi-zone approach, how do you ensure proper ventilation air distribution?
So that's a very good question, and one that I have talked to our staff that work on new home certifications. So the question is that, most new homes now are using HRVs or ERVs, and they connect up the distribution or the ductwork on supply air and exhaust air into the central air distribution system. So they could either be both in the return or in return and supply. And in theory, the way those are supposed to operate is that either the HRV and the air handler run continuously, or depending on the sizing on the HRV, it may run for a fraction of the hour. And in those situations, the HRV should be interlocked to the air handler, so the air handler runs at the same time. Now, how you get that to work with the multi-zone system, I'm not quite sure. I haven't been able to get an answer to that question. You would think that maybe when heating and cooling isn't required and the HRV is operating, that you would like to have all of the supply dampers open so that you get that ventilation air evenly distributed throughout the house. But then when you have heating and cooling and say only one supply air damper is open, then potentially most of the ventilation air would be provided to that zone and not others. So I think there are some issues regarding the connection of the HRVs, ERVs into the central air distribution system and how that impacts ventilation that really need to be addressed.
Thanks. Another question we have, you mentioned the adoption of mini splits as one of the potential limiting factors of the potential market for multi-zone systems. Did you look into lower cost smart vent technology at all, where there are dampers and supply registers in each individual room?
Yeah, we did not consider that as an option, and I believe some programs have looked at that. I think there has been concern with those systems that I think you can provide the control that you may want to each of those kind of rooms. The concern is that very often for Minnesota central air distribution systems, we have less airflow through the furnaces or heat pumps than they were designed for. And if you start closing off supply air registers in individual zones, then you're going to further restrict the airflow through the furnaces and the heat pumps, and then potentially reduce that enough so that you could impact the efficiency of the furnace and the heat pumps. You're also going to kind of increase the duct pressures. So fortunately for us, in Minnesota, most of the ducts are within the envelope, so increased duct leakage isn't as much of a concern unless some of the ducts are outside the envelope. And that's the concern that they've had in warmer climates when they have ductworks outside. So to my knowledge, the 5 utility programs that looked at zoning systems, at least a few of those were using the smart vents. And I know there were concerns about the restriction of airflow through the central air handlers.
Thanks. Another question we have, did you find with any of the houses you studied any issues related to unbalanced supply and return? How much of an issue do you think that could be in existing or even new homes?
We didn't look at that issue, and I think I may have mentioned it at one point, but for most of these systems or all of the systems, there are dampers on the supply ducts there aren't dampers on the returns. So potentially, if you have a supply branch going out to the basement, another to the first floor, another to the second floor, you will be controlling the supply airflow, but you're still going to be returning air from each one of those zones. So in those configurations, you control the amount of heating and cooling that you're providing, but that when you have all the returns open, um, you're going to be kind of further mixing the air within the house. And I think you are correct that if you have, say, doors between the basement and the first floor, you could create situations where, you aren't supplying air into the basement, but you have return air. So you could be depressurizing the basement and potentially causing some additional air infiltrations into kind of zones that are not open to each other. So I hope that answers that question.
Yeah, thank you for that. Another question I see, I think I heard earlier in the presentation that zoning on the return wasn't looked at. Is there no merit to having zoning included on the return to adjust in conjunction with the supply to help keep temperatures balanced and reduce overcooling or heating?
Yeah, it ties into the previous question. So I think there is merit. Again, you potentially would address any concerns about depressurizing or pressurizing zones and impact that might have on air infiltration, exfiltration, kind of driving moisture into walls and so forth. The and kind of mixing of air within the house. To my knowledge, these systems are always just installed on supplies. I suppose you could use the dampers on returns, but then you would also need to make sure that all of your return ducts are configured in the same way as the supply ducts, in that you have, one return branch coming back from each of the zones, so that you could install the damper back there at near your central air handler. And I know for existing houses, one of the concerns about implementing zone systems is whether the ductwork is actually configured so that you could, zone those to the um, so that the branches go off to the separate sections of the house where you want to do the zoning. And I think often in older houses that isn't the case, and you would potentially need some reducting in order to make that happen for older existing houses. And I think the similar might happen for the new houses, that you'd have to look at different configurations on your return duct runs in order to do the return damper installation.
Thanks. One question I had was, what is the typical cost of a multi-zone system compared to a single zone system?
So unfortunately, when we were interviewing our contractors, we didn't add that as one of our questions. So we are going back right now and contacting the contractors that we interviewed and see if they can provide that information, and then we can include that in the final report. So a little bit of a teaser for the final report. I recently did talk to a developer that are using, let's see, they have multi-zone systems as an upgrade option in their townhomes, and they indicated that the added cost for a two-zone system is about $2,500 for them, and about $5,000 for a three-zone system. So it's not an insignificant cost to be upgrading from a single zone to multi-zone systems.
Thanks. What are the considerations for applying zone system in a retrofit situation?
Yeah, so as I kind of mentioned in one of the previous questions, I think with new construction, you have the ability to design your ductwork so that the branches go out to each zone that you want to control. in existing homes, that often wouldn't have been considered. And so the branches may go off into one half of the house where one branch might um, um, supply, say, the east side of the house, both the basement, first floor, and second house, and then another branch might go off to the west side. So that's not really conducive to the type of zoning that you would want to do. So the question will be is how often in existing homes is the ductwork set up so that you could install the zone dampers, the supply air dampers, without having to reconfigure the ductwork and give you the kind of control that you would like.
Thanks. And sort of the last question I have here is, you mentioned that 5 utilities had pilot projects for zone system. Is there any more specific information you can share about these pilots based on your interviews?
Yeah, unfortunately, in none of those cases did they publish any information, and in many cases there's really very limited report or information provided. At least a couple of those were involved smart vent zoning, which another user referred to. So I will say the information on the utilities that had pilot projects is included in the final report. The ones that we found were Enbridge Gas, PG&E, Sacramento Municipal Utility District, Consumers Energy, and SoCal Gas. So those would be the utilities to contact to try to get additional information. In general, I think those were primarily looking at the smart vent zoning where they're controlling individual registers.
Thanks, Dave. Mary Sue, I don't have any additional questions.
Great. Thanks, Adoy, for managing those questions. There were a lot of really good questions there, and thanks, Dave, for answering them all. And for your presentation. If you do have follow-up questions about this card project, feel free to contact Dave or myself. The recording of this webinar and slide set will be available on the department's website in a few weeks, and the final report in probably a month or so. When available, you can link to either of these from the quick links on our Applied Research and Development page, which is indicated on this slide. The R&D page has lots of other information related to CARD and the CARD program and to research projects, so you can check that out also by going to the link at the bottom of this page on the slide. Bottom of this slide is what I mean. Thanks for your participation today, and we really appreciate your interest in CARD. And before I close, I'd like to just remind people of some upcoming CARD webinars. On April 13th, the Center for Energy and Environment will be back to report on the results of a 3-year DOE and CARD-funded project that demonstrated and assessed the energy and non-energy benefits of power over Ethernet technologies at 4 commercial institutional sites. Then on April 28th, Franklin Energy will join us to discuss the energy savings potential of network lighting controls and the challenges of deploying them in small businesses through real-world projects. You can keep abreast of upcoming webinars and other news related to the Minnesota Conservation Improvement Program by signing up for SIP updates on our email list. You can use the link on this slide to do that. In the meantime, feel free to contact me if you have questions or suggestions for the CARD program or for CARD webinars. And also, as a final reminder, there'll be a short evaluation that launches after this webinar. Please take a few minutes to fill it out and let us know how we did. Thanks so much, and I hope you enjoy the rest of your day.